Before we begin, here's a quick message. I know many of you are on YouTube to see something relaxing or enjoyable, and these videos are decidedly not relaxing. But problem solving is just like that. Solutions don't appear immediately, and I'm trying to share more about the discovery process behind the solution, not just the solution itself. So to make the most of this, pause and think before listening to my solution discussion. And do stick around till the end. Don't give up just because the questions look difficult at first. Thanks, and enjoy the rest of this video. If you have seen the last video, you'll be aware that we talked about how to get a better view of a problem by zooming in and out. We mentioned zooming into notable specifics, zooming into separate cases, and zooming out to see the big picture. And if you have tried my suggestions so far, I hope they have provided some insights and observations. But once again, there may be two issues. What if I don't know what to do with my clever sounding observation? And worse still, what if I really don't spot anything at all? In this video, we'll look at an idea that's mathematical but also somewhat psychological, wishful thinking. To assist our memory, I'm going to call this the MAD approach. M stands for maybe. Maybe the problem is simple. Let's use some wishful thinking. A stands for assume. Assume something convenient that makes your problem easier. And finally, D stands for do. Do something related that you know is simple enough for you, and then hope for the best. The first point is at the very heart of wishful thinking. Maybe this question is simple, and ask yourself, what would resolve this problem very easily? And then we check whether that actually happens. So here's a simple example that illustrates this. Let's say we're asked to evaluate this product. The first thing to ask yourself when you see this or any other problem is, what could be the best case scenario for me? In this instance, where you have a product, the answer is hopefully one of the factors is 0. That would be wonderful. Are any of the factors 0? Thankfully, tangent of negative 45 is negative 1. And so one of the factors is indeed 0, and so therefore the entire product is equal to 0. So this is what we mean by thinking maybe the question is very easy. Now here's a question that comparatively is less straightforward. Essentially, it asks you what is the fewest number of cubes you need to sum up to 2002 to the power of 2002. Naturally, this question is taken from some competition in 2002. Note that negative integers are allowed, so we can technically subtract cubes and not just add them. I'll pause to let you think about this for a moment. If you are stuck, let me remind you of the section header. Maybe it's simple. So let me ask you a question. Which of these do you think is easier if we're trying to prove the result? To answer this question, we need to think about what needs to be done to prove t to be something small like 2, and what needs to be done to prove that t is something large like 200. Supposing that 2 is optimal, here's what you would need to do. You would need to tell me which 2 cubes sum to 2002 to the power of 2002. And then you need to explain to me why 1 cube isn't sufficient. In other words, tell me why 2002 to the power of 2002 is not a perfect cube. Conversely, suppose that you are trying to show that t equals 200 is optimal. you need to give me 200 cubes that sum to 2002 to the 2002, and then you need to explain to me why 199 cubes or less are insufficient. And that sounds pretty much hopeless. Even if you could give me 200 cubes, why isn't 199 enough? Now remember what we mentioned in our first video. These are solved problems and the method is supposed to be reasonable. So we can probably guess that he is quite small, and we should try to write 2002 to the 2002 using just a few cubes. Admittedly, this number is certainly too big to handle directly. So let's get our hands dirty and try to split up 2002 into cubes. How many cubes do you think you need to form it? If you're observant, you may have realized that this can be just 1000 plus 1000 plus 1 plus 1. And this only uses 4 cubes, which sounds like a pretty good deal already. Now, let's zoom back out to the original number and ask ourselves, can we extend what we just did to 2002 to the power of 2002? If you haven't already figured this out, please think for a moment before carrying on with this video. Have you solved it? The answer is yes. We can factor out 2002 to the power of 2001, because that's a cube since 2001 is a multiple of 3. As a result, we can factor out 2002 to the power of 667 cubed and write 2002 as the 4 cubes we saw earlier and regroup them together into these 4 cubes that sum to 2002 to the power of 2002. Let's assume for now that is the correct answer for want of a better idea. In other words, I need to show that 3 cubes cannot sum to 2002 to the power of 2002. Think for a moment. What kind of argument could possibly show that something like this is actually impossible? Personally, my first instinct would be to use modulo arithmetic. And the reason is that any bounding argument is unlikely to work since I'm allowed to pick both positive and negative cubes. The issue is that it isn't immediately clear what modulo to apply. However, we do know that in order to show that something is impossible to express using 3 cubes, we want to find a modulo such that cubes have only a limited number of possible values. So let's get our hands dirty, check some small values of n, and see whether any of them seem to pop up. The way to check this is rather boring but straightforward. For example, if we want modulo 5, we just check 0 cubed, 1 cubed, 2 cubed, 3 cubed, and 4 cubed modulo 5 and list out all of these values. If you have done that, perhaps until something like 10, this slightly annoying work, but you would have got something like this. Now it seems to stand out that for 7 and 9, there are only 3 possibilities, negative 1, 0 and 1 modulo 7 or 9 respectively, and those are the most constraining looking ones among this list. So hopefully, up to 10 is good enough. To know which of these 2 are a better choice, I should check what is 2002 to the power of 2002 modulo 7. That's 0, because 2002 is divisible by 7. And I also should check it modulo 9. It turns out to be congruent to 4 modulo 9. Now that stands out to me because I'm trying to use 3 cubes that can only be minus 1, 0 or 1 modulo 9. And they are supposed to sum to 4 modulo 9. That certainly is not possible. So we have found the suitable modulo, and this completes our proof, which is that 3 is not possible, 4 is possible, and so the smallest possible t is equal to 4. Now that you have solved the problem, I can reveal to you that this problem was from the IMO shortlist. I'm not sure whether the viewers of this video generally find that IMO shortlist problems are easy, but I'm fairly certain there are some of you who do not. So the moral of the story is that don't let the reputation of a competition stop you from doing some wishful thinking. For the next kind of wishful thinking, imagine you had a hypothetical mathematical genie who could grant you a wish. What would you wish for mathematically? That's exactly what you should assume. Ask yourself this: is there some special case of the diagram, or some special constant or special significant value that you could use that makes things easier? Then assume that, especially if it's allowed within the conditions of the question to assume it. This next problem is taken from the exceptional Twitter feed of Catriona App, who regularly posts original geometry puzzles which are also aesthetically very attractive. Most of them have a rather simple premise, including this one: arrange 3 squares as shown in the diagram and find the marked angle. And for us, let's start by thinking about how to get the answer only if there is no requirement of a proof. To proceed further, we need to ask ourselves this: what makes this diagram, well, this diagram? To put it into words, there are 2 features. The pink and the green squares share a side, and the yellow square shares one of their common vertices. Now, think about this. What assumption would really help? The answer? Arrange the squares something like this. Notice that this is actually allowed because the pink and green squares still share a side, and the yellow square still shares a vertex with the other 2 squares. So this is a valid configuration, but it is now very clear that the answer is 45 degrees, and so that would at least give a numerical value for this problem. But let's try to solve this question now with proof, armed with the knowledge that it is actually 45 degrees we are looking for. So think for a moment. Why doesn't the angle change as I move the yellow square around? Let's superimpose the 2 diagrams, the ideal one and the one that we currently have. Based on my labeling, we believe that angle ABD and angle ACD are both 45 degrees, and so this would mean ABCD must be concyclic. But why should that be the case? If we think about this, there might be a few possible explanations. Here's the easiest one. Call this point O, and that means that OA, OB, OC and OD are all equal to square root 2 times the side length. And so that means that O is the circumcenter, and angle ABD is half of angle AOD. Angle AOD is 90 degrees, so angle ABD is 45 degrees. Now notice that now we can even remove the point C, and our proof would still work. But how the assumption helped us is to guide us to the correct approach. Even if it would not have been so obvious, we should have shown something like O being the circumcenter of ABD initially. Now, our final approach is kind of like reality setting in real life. Sometimes we actually need to stop daydreaming and tackle some concrete tasks first. So ask ourselves, is there anything related which I can tackle? And then the wishful thinking is that hopefully these 2 vaguely related problems are more related than I initially thought. So here's my final example. Essentially, you're asked to sum up all the reciprocals of squares of odd numbers and estimate this to one decimal place. That's what floor of 10s is really asking for. Now pause for a moment to think of what related but simpler problem, in your opinion, that you can solve. One possibility is that you're pretty mathematically knowledgeable and you remember this sum, which in itself is really interesting and can have an entire video talking about it. Now if that's what came to your mind, ask yourself this: how do I get from here to my sum s? It turns out this is easier than one might think, because we can split up that known sum into the sum I want and the same sum but with even numbers in the denominators. Why is this useful? Because the one with even numbers in the denominators can just be written as 1/4 of that same sum we already knew. Therefore, we can conclude that pi squared over 6 equals to s plus pi squared over 24, and s is pi squared over 8. For the specific question, let's just find it to one decimal place by bounding pi between 3.1 and 3.2. So s would be 1.2 something, and the value is 12. You might protest and say, hey, that's not fair. I didn't know that strange sum that you just showed me earlier. Alright, then let's say that you did know how to sum up telescoping series of fractions using partial fraction decomposition, such as this classic one shown here that many of you have probably seen before. Ask yourself this question then: what telescoping series could be useful to compare to the series given by S? There's no specifically correct answer for this question, but since we have odd numbers, maybe one of the things that could come to mind is this series. Now, this series is also not very difficult to sum up because with an extra factor of 1/2 on the outside, everything on the inside cancels off and the sum is just 1/2. Ask yourself this question again: how exactly is this sum related to the sum S? Now ideally, we'd like to say how close they are. But first let's check which one is larger. Comparing term by term, it's pretty clear that 1/1 squared, 1/3 squared, and 1/5 squared are larger than the respective series terms from S. So this implies that S is more than 1/2. But that doesn't sound very good because we expected that S is quite a lot more than 1/2. And looking back at this, it kind of makes sense. Why? We compared y with 1/3, 1/9 by 1/25, so these are really quite far apart. So most of the inaccuracy comes from the front, and in order to fix that, let's just improve by only estimating the third term onwards while leaving the first two terms exactly as they are. We can work through the telescoping series now almost as easily. It is equal to 1/10 with the two fractions that we left there at the front being 10/9. Expressing this as a decimal, we get 1.21111 as our lower bound for S. But we're not done yet because we don't know that S is much bigger than 1.21. It could be something like 1.5. So to round this up, we need to also establish an upper bound on S. Thankfully, we don't need to do anything too clever to get this upper bound. If we do things similarly, except that we make the fractions bigger instead, we'll get a rather similar looking telescoping series, and this time the sum would be 1.277777. So even though we didn't find the exact value this time, our conclusion is that S is between 1.211111 and 1.27777, so that's good enough to give me the floor of 10S. I want to conclude here, but here's a bonus question for those of you who know some calculus. Can you solve this by comparing this sum to some appropriate definite integrals? If you're thinking of integration, then this could be a third possible way to solve this problem. And I'll leave that to you. Please comment below if you have an idea how to do this. So, remember, it's okay if a problem drives you mad, as long as you remember these mad steps. In the next installment of our series, I'll attempt to tackle another thorny question. Am I getting closer to the solution? I don't think I'm able to give a complete answer, but as usual, I'll try to offer a few useful ideas. If you found this video helpful, please subscribe to my channel and do check out some of my other videos where I go through contest problems at perhaps a more conventional pace. Thanks for watching, and thanks for waiting. See you again next time.